All right, so here we're going to start dealing with percentiles and quartiles. So a z-score measures a data item's position in a normal distribution. Another measure of data item's position is its percentile. Now, percentiles are often associated with scores on standardized tests. So you might have seen on a test you've taken, why does it keep changing? Uh, that you got into the 75th percentile or the 44th percentile. So in this case, if we got into the 45th percentile, that means that 45% of the scores are less than this score. And if you score in the 95th percentile, it means 95% of the scores are less than this score. So the higher you get, the better your score is, because that means there's a lot more people below you than if you were, say, at the 45th percentile. So for percentiles, if n% of the items in a distribution are less than a particular data item, we say that the data item is in the nth percentile of the distribution. So for instance, in this case, a student scored in the 75th percentile in SAT. What does it mean? Well, that means 75% of the scores on the SAT were less than this student's score. Okay. And again, it all boils down to it's the 75th percentile. And so 75% of the students scored less than that on the SAT. So that person was better than 75% of the other students. All right. Another thing we could look at besides percentiles are something called quartiles. Now, three commonly encountered percentiles are the quartiles. So these are actually percentiles, but there are specific ones called quartiles. And quartiles divide data sets into four equal parts. The 25th percentile is the first quartile. So that's this piece here. That's the first quartile. And so that's at this point is the first quartile, or the 25th percentile. Then we move up, the next one up, that goes to the second quartile, which is our median. And that's going to be the 50th percentile, because now 50% of the scores are less than that. And then we could go into the third quartile, which is the 75th percentile, and 75% of the scores are less than that. And then we really don't mention the 100th percentile or the fourth percentile, but that's going to be the rest of the data. And so that's going to be what it is. So what we're doing is we're splitting it into equal parts, 25, 25, 25, 25. And so depending on what part you're looking at, depends on where you're at. So again, it goes, the first 25% is going to be the first quartile, or the 25th percentile. Then if we go all the way up to the mean, which is the median, that's going to be the second quartile, or the 50th percentile. And then if we go up to the third quartile, or the 75th percentile, that's 75% of the data is less than that. And then the other way is it's going to be the whole set of data. So that's why we don't mention what that is. All right. So here we have poles and margins of error. So statisticians use properties of the normal distribution to estimate the probability that a result obtained from a single sample reflects what is truly happening in the population. Now, if you look at the result of a poll like the one shown in figure 12.22 here below, you'll notice that there's a margin of error reported, and that's at the very bottom, and that's usually how it is. It's going to be down here, and the margin of error is plus or minus 3.2%. Now, surveys and opinion polls often give this margin of error, and so let's use our understanding of the normal distribution to see how to calculate and interpret the margins of error. So this is going to be a lot of showing you how to do the calculation, but what we really need to do is we get that final equation at the end and we can utilize that. So a lot of this stuff we're going to look at first is just kind of how to get there. All right, so suppose that P% of the population of US adults dread public speaking. Now, instead of taking only one random sample of 1,000 adults, we repeat that process of selecting a random sample of 1,000 adults hundreds of times. Then we calculate the percentage of of adults for each sample who dread public speaking. Now, with random sampling, we expect to find that percentage in many of the samples is close to P%. Okay, so that's kind of the key here. With relative few samples, having percentages very far from P. Okay, so that's going to be the key. We're not going to be too far from it. Now, figure 12.23, which is over here, this slide here, we'll talk about it, shows that the percentage of U.S. adults who dread public speaking from hundreds of samples can be modeled by a normal distribution, which is what we've been working with, so that's good. Now, the mean of this distribution is the actual population percent, P%, who dread public speaking and is the most frequent result of the samples. Now, mathematicians have shown that the standard deviation of a normal distribution of samples like the one found in figure 12.23 is approximately 1 over 2 times the square root of n times 100%, where n is the sample size. Now, if we use the 68, 95, 99.7 rule, like we've done before, we split it up. Approximately 95% of the samples have a percentage within 2 standard deviations of the true population percentage, the P%. So 2 standard deviations is going to be 2 times this value up here. So 2 times that. What happens is those two cancel, and we get 1 over the square root of n times 100%. Okay, so this is where I'm telling you, this is a lot of math to get to where we're going to get to, but now we have that up here again to kind of show that it's canceled. Now, if we use a single random sample size of n, there's going to be a 95% probability that the percent obtained will lie within 2 standard deviations, or the 1 over square root of n times 100% of the true population percent. So we can be 95% confident the true population lies between a minus or a plus 1 over square root of n. So it's going to be somewhere between here and here, which is 2 standard deviations away from the mean. So there's 2 standard deviations away from the mean either direction, okay? Now, what we do is we call that plus or minus 1 over the square root of n times 100% the margin of error. So what we do is we just have to plug in here our n, which is our sample size, and we can get the margin of error. So, in a roundabout nut case here, if a statistic is obtained from a random sample size of n, there's a 95% probability that it lies within 1 over square root of n times 100% of the true population percent, where plus or minus 1 over square root of n times 100% is called the margin of error. So that's going to be what we're going to use to do calculations. So here it says Harris poll of 2,513 U.S. adults aged 18 and older asked the following question: how many books do you typically read in a year? Now the results are shown over here. And so what it wants us to do is find the margin of error for the survey, round to the nearest tenth of a percent. Well, we know that the margin of error, we'll call it ME, is equal to what? Well, it's 1 over the square root of n. Well, n is 2513 times 100%. And so now we just have to plug that into our calculator. And we get 1.9948. So we get 1.9948%, but to the nearest tenth, well, that 9's going to round that up. So this is approximately 2.0%. Okay. Now we need to write a statement about the percent of U.S. adults who read more than 10 books per year. Well, what did we say about this? Well, we said we were 95% confident that between 34% and 38% of Americans read more than 10 books per year. Okay. And so that is giving us that, because if our standard deviation was going to be that 1, and then it's going to be plus or minus that many. And so we're between the 34 and 38, is the 2 standard deviations each direction. And so that's what that's talking about. So 2% each way. And so that's why we have the 34 to 38. And we're 95% confident because that's how we got the calculation. Now, C, why might some people not respond honestly and accurately to the question in this poll? Well, mostly because, well, I won't even write this, but they're going to be embarrassed if they don't read at least 10 books a year, or maybe they don't even read any books a year. So if they think you're wanting to hear something, they're going to say, hey, I read, 15 books per year, 20 books per year. So there's going to be some people who are not answering honestly or accurately because of that. Another reason why they might not keep track of how many books they read per year. So those who do read a lot of books, they're going to be, well, there's a lot, and I don't know how many it is, but I'm pretty sure it's more than 10. And so they'll say, yeah, I'm doing over 10. So there's a lot of different ways you can put that one. And so I'll leave it with that as far as you can go either way. You don't know how many you read, or you just don't want to say, I really don't read any books. All right, so let's stop there and we'll come back for some more.